Good morning, Miriam.
Good morning, teacher.
Did you receive yesterday initial
Yes, teacher.
to start and to make a calculation? You can uh, go to Google Disk and download tutorial with examples, and you can look at example and make calculations the same but with your initial data. How to find Google Disk? You should come to 202. It is a channel name 202 space XAI, English letters. You'll come here and here in a banner you'll find a link text. When you go to this link, you can open DME, home task, ScrewNut V22. Is it clear?
Yes, teacher.
So you can open the example and make work as it shown in example. Wei,
Yes, teacher.
good morning.
Good morning.
Mariam, you should download workbook. It is a file, PDF. I show you where is it. In DME, file is named workbook P122. Here you'll find tables, pictures, drawings. You should use it for calculations. Yeah. Maybe 2-3 minutes waiting for those who late, and you should try to download this workbook, okay?
Okay.
Please. Hajar,
Yes, teacher.
why you didn't send me email?
I will, teacher. I forget yesterday.
I remind you.
Okay.
Look, you should come the same way as Miriam. Open YouTube channel 202XAI English letters.
Can you write this in chat?
Name
Yes.
when you come to this channel, you'll see picture like this. And here you see texts. What do you use, phone or laptop?
Phone.
Phone. And when you come to this channel, let's go at this names and about channel. This link is not usually is not seen on phone screen, but you should come to about channel and you'll see this link. Yes? Have you found this link?
Wait.
Boris? Boris?
Yeah,
Did you get my letter?
yes, I have received.
Okay.
Okay, it's fine.
Do you have a workbook?
I think we have to find it on Mentor. We can find it.
Sorry. I'll tell your classmates how to find it. What do you use? Phone?
We must go through Mentor through there to find.
Teacher, I found
Yeah.
this channel.
Okay. About channel and find the links.
So, excuse me, sir. Where do we have to go to find it?
Yeah. I send you right now.
Okay, thank you.
I sent.
Okay, thank you.
Miriam, I sent you an email. You got it?
Yes, teacher. I already find it.
So I think that it's all. So today we make laboratory work number 4. Just a moment, I switch on my screen. Laboratory work is about experimental analysis of forces in bolts. I told you on lecture that usually we use treated joints when we need to save any volume from penetration from outside or from inside out. I told you that it may be cylinder with cover, and we usually need to avoid a gap between cover and cylinder. But sometimes when we have a static load, we should not try to make connection without gap. It may be because this load is not dangerous for fatigue endurance. So to know what forces we apply to our bolt joint, we should consider calculating scheme like this. We have a bracket, something like bracket. This is a bracket. And this bracket is loaded with force directed in any direction. And in such case, we have two components, Fy and Fx, which load both bracket and bolts, which fix this bracket in their position. Let's consider connection where we have 3 bolts. 1, 2, 3. 3 bolts. And consider the force which will try to load our bracket in 2 directions. Fy tries to elongate bolts, and this force is distributed the same for all bolts. And Fx, this force creates a moment, Fx times distance h, we have moment. And this moment also should be added to to force, which will be like reaction on this Fx. But in our case, when we try to consider force components only, we can use K. It is a thrust fillet, which fix bracket in their position, and we have here a reaction, and this reaction equals Fx. So it means that our bolts are not loaded with a force which try to shift bracket relatively to the base. So such design is widely used. That's why let's consider how to find the bolts, the forces into these bolts, to know is this bolt enough to take load or not, and what bolt limit value should be, and how to compare acting force with limit force. Okay, so what's happened with our joint in a case when we have such load? According to this mechanism, when we don't have shear stresses into the bolt, we can consider our mechanism like a body which is loaded with moment only. According to this moment, bracket tries to tune around a specific point. We discuss what point. And in places where we have bolts, we have deformations. Deformations for first bolt, and second bolt, and third bolt. These three deformations are similar. If you remember from geometric, that the bigger distance from center of rotation, the bigger deformation. This deformation, in our case, it is this deformation of bolts. Each of them is loaded with force, and this force creates deformation. So it means that if we have three deformations, each of them is proportional to the distance from center of rotation. We don't know initially what place should be considered like center of rotation. That's why we should consider some variants. And the first of them, we consider case when rotation is about edge of bracket, and the point I show you right now here. In such case, we have deformations in each bolt, into each bolt. According to this diagram, we know that we have three forces. It means that we have three unknown parameters. And to solve this task, to this problem, we should make some assumptions to make it easier and to make it calculatable. So to make it easier, we think that after applying an external load, contact surfaces of connected component remain flat due to their big rigidity and rather small rigidity of bolts. It means that we consider bracket absolutely rigid, which is not deformated. So deformation deals with bolts only, because bolts have smaller stiffness, that's why can be deformated. Then first case we consider that bracket turns about the edge of its base. It means that we have rotation about this point. So according to this assumption, deformation A, each deformation proportional, I said, to the distance. And forces and bolts can be determined depending on each bolt deformation and rigidity. We considered in lecture that we have deformation. If we have deformation, we have force. If we have a force, we have deformation. So in such case, we can solve this problem. So unknown forces F1, F2, and F3 may be written in this form. Moment equals force 1 times A1, F2, A2, F3, A3. We don't know, we know A1, A2, A3, but we don't know F1, F2, F3, three unknown parameters. It's one equation we can use, and so-called deformation compatibility condition. It means that if we have bigger distance, A1, we have bigger deformation. And similar triangles give us opportunity to use this formula second, and equation like this third. Then we don't know deformations. So if we know that deformation equals force times L divided by EA, and the same for 2 and 3, they are free elongations. And if we use this formula, and we know that A areas of the bolts elasticity modulus also the same, so we use the same material. It means that we have E and A the same, and L length L1, L2, L3 deformation lengths. In such case, we can write in this formula, instead of delta divided by A, F, because here all other parameters are the same. We can neglect it. We can reduce it. So the bigger distance from the edge the bigger distance from the axis of rotation, the bigger force should be. If we use this equation and take F1 from this equation, put it in here, take F1, F2 from this, and from this we have one equation about one force. And the same way we can write for second and third bolt. If we used there this equation, equilibrium condition, so we can use formula like this to find force according to moment we apply. Let's consider our set and describe their parameters into the workbook. Open your workbook. Who have this workbook, who don't have, use a paper, write parameters, and after that rewrite in workbook. So external load, let's take it 7,000 Newton. 7,000. Shoulder, distance distance from the face to the point of application, force application. It is 300 millimeters. Force shoulder 300 millimeters. Next, moment. Moment is force times shoulder. M Fx times H. We use laboratory set which create Fx only. Fy in our experiment equals 0. That's why force I gave you, it is a force Fx. They are the same. It means that to find moment, we need to apply multiply 7,000. I said 3 times 300 millimeters. It should be 2,100,000. Distances between bolt axes. A1, this distance is A1. This is distance from edge to axis of the highest of bolt. This is A1. A2 is the distance from the edge to the axis of the mean bolt, it's A2, and A3 is the distance from the edge to the axis of the lowest axis, of the lowest bolt. They are distances A1 180, A2 100, and A3 20 millimeters. You see, pitch is the same, 180 minus 100, distance 80 millimeters, and 100 minus 20, also 80 millimeters. So distances are the same. So A1 180, A2 100, 20. Length of the bolt 265. Bolt material, bolts material. Steel ST free. E is 215 times 10 power 5, and bolt rigidity 625 times 10 4. It's very interesting how it should be. Let it be like this. I tried to find where is the subscript. And 625. I write it like it. So, like this. Then, equipment number 1 is indicators. indicators. 1. Number 2, bolts. Number 3 is a bracket. Number 4 is a tension screw. Tension screw we use to create load. To measure this load, we use dynamometer number 5. And number 6, bed or rack or base. One, indicators. 2, bolts. 3 is bracket. 4, tensile screw. 5 is the dynamometer, and rack or bed of frame. Number 6. You should write here. Bolt sketch. This picture. Let's you draw this bolt diagram at home. Or if we have time at the end of class, you finish it later. Let's continue. So, we considered laboratory set, and now next stage it is a order. We should load our bolts and compare, after that, compare these bolts loads with calculated value. So let's make it calculated. You should use this formula to find forces. 1, 2, 3. Moment 2,100,000 Newton millimeters. AI, it means that A1, A2, A3. And this parameter changes, and in denominator A1, A2, A3 are the same. Are stable. This parameter does not change. So we can calculate this plus this, and m divided by these parameters. So after that, you write calculation results here. We consider first variant when turnabout age So I hope you calculated. All right, please, who calculate first force? No one who calculate? First force may be calculated like this. 180 look. It is a first force, F1. These parameters are not changed. That's why we can calculate it like coefficient. $180 and squared it. 10,000 plus 2,400. So approximately 50 times 180. $8,820. Is the first. And the same way you can calculate F2 49 times So first force is 8,830 approximately. Second one 4,900 and F3 approximately 1,000. So we have forces which act in bolts after the applied force for 7,000 newtons to break it. It's the first variant when we have edge, and another one axis. What does it mean, axis? Because we don't know where is correct place of axis, we consider second variant, when bracket turns about the axis of the lowest bolt. In such case, we can calculate forces if we know that A free distance equals 0. and we need to take distances. I said here that distances are the same. So it means that 180 minus 20 is 160, and A2 minus A3, it is a 80 millimeters. The same distances like in previous case was 80 millimeters and 80 millimeters, but we should calculate shorter shorter calculating example. In such case, instead of A1, we need to use A1 dotted. It is A1 minus A3 and A2 minus A3, and A3 equals 0. So it becomes shorter, and to find these forces, we should use formula like here. Instead of AI, we should use AI dotted like this. The same calculation. The only difference is that F3 equals 0 and F2 should times 80. And here we have two components, A1 minus A3, A2 minus A3. So it means AT but 0. And here, 49 instead of 49 should be something else. 160 squared plus 66. So it is for you. You can calculate it at home. So, in such case, we have two variants. One is when we consider tuning about edge, and second variant when we consider tuning about the axis of the lowest bolt. Now we should try to make experiment, and after that measure and calculate experimental values and compare with calculated cases. Take a paper and fix, write results of readings we will have during experiment. Our laboratory set looks like you see here. It is it's made maximally rigid. So you see here T-shot T, T profile. Here bracket, screw, dynamometer, bed. You see indicators, bolts from this point to this point. This is long and thin bolts. 1, 2, 3. Here we have a nut and screw, and when we rotate, we create axial force. This indicator shows us how many millimeters of deformation we have during loading. Pay attention that we have one revolution, and big arrow shows us tenths, hundredths part of millimeter. So you see that scale is 0.01 millimeter. And to make load 7,000, we should rotate nut up to situation when big arrow makes 7 revolutions. We have now 1 revolution. The small arrow shows how many full revolutions was made by big arrow. So 1 revolution, 1 more, 2, 1 more, 3. We need to create a load 7,000. 1 we have on indicator plus 7, it should be 8. It means that we should rotate nut up to state when small arrow shows 8. So let's go. We started from 0. here we have connection with bed. And you see that here we have very rigid frame. And here you see K. It's the thrust fillet to avoid motion of the bracket under the force down. And indicators also. First bolt, second bolt, third bolt. All of them shows 0. When we rotate the nut, arrow moves, and this small arrow shows full revolutions. So we need to make it up to 8. Eight revolutions, so load 7,000. So check. So first reading, arrow was in this position. Now it moves clockwise, and the maximum dimension or reading is 5, 15, 16, approximately 17 points. It is not 17 millimeters or micrometers. It is 17 points. It is test 1, bolt number 1. This value is 17. Second, 5, 7, 7.5. Let it be 7. Pay attention that first and second bolt have deformation when arrow moves clockwise. And third, you see that arrow moved and counterclockwise, and approximately 3 points. 3 points when in another direction. It means that we should describe it by means of sign. Here we should write this, it minus 3. After that we unscrew. up to 0. Sorry, quality should be 0, and repeat loading up to 8. What we have here, the same 17, here 5, here -3. -17, 5. So usually values close to the same. That's why we made 2 tests, and the average value is 17. Here 6. -3. Bold deformation. I said that it is a reading, it's a point, but you saw. I hope you saw that 1 point means 0.01 millimeter. So if we need a result in millimeter, so it means that we should times to scale 100. So it means that bold deformation (17) forces. To find forces, we should use formula like this. For each bolt, the stiffness times deformation, and we'll have force in a bolt. CB 625 10⁴. So you need to calculate 3 times. Here times 17 times 6 times 3. So we have 3 values. Now you should put here on graph, you should put 3 lines. 2 of them are calculated when we considered tuning about H, and second variant about axis. You'll do it at home. And third line is according to experiment. So maximum value is about 11,000 kilonewtons. So what we have? 2, 4, 6, 8, 10, 11 here. the first point. Second, 3 and 7. 2, 3, and 7 approximately. It's approximately here. And third, 108, but in so sorry. Very difficult to draw. By mouse. No. Something like this. And you should add 2 lines according to calculations. This line, 3 points, and first, second, and third bolts. Here you calculated home, and third, you see. Maybe your graph will be beautiful, not like mine. Conclusions. Some words about conclusions. First, conclusion you can write about calculation result. Is our calculation close to the experimental or not? When you draw 3 lines, you'll see what calculation is closer to the experimental one. It's a first. Which calculation is better describe state of force? It's a first. Second, you'll see that this line is not straight line, not because my difficulties, because it is not linear. First 2 are straight lines. They are the same difference between first and second and third. In our case, in calculation, it is not straight line. So it means that we should take into account flexibility of the all elements. According to our assumption, I said that the assumption is we take we consider all elements absolutely rigid, but they are not rigid. They have some flexibility, and under the load we have deformation not only of the bolts. Bolts, it's a main part for deformation, but it is not the only element which was deformated in experiment. So it means that our assumption not play shows us show that real state is not absolutely rigid. And third, may be done that tune axis of bracket is not at the edge at the last axis of the third bolt. The real tuning axis is higher. It's between second and third bolt. So real state is like here. Relatively good calculation. That's why I think that we can use this methodic, this way how to calculate correct bolt joint. Okay, so that's all I would like to tell you today. Do you have any question? When you finish your work, send me workbook. I'll check it and return you it if you correct, or with questions if it is not correct. Questions? No questions. Okay. In such case, goodbye. Hajar, I'm waiting for your
Okay,
letter.
teacher. Goodbye. Thank you so much.
Send me your mail, please.
Okay.
Goodbye, teacher.
Goodbye.